For one more example of what we can do with all of these ideas surrounding eigenvalues and eigenvectors, let's have a look at the Fibonacci sequence. So just in case you've never heard of the Fibonacci sequence, it's a list of integers, so a sequence of integers starting with 0 and then 1. And then you continue this sequence by adding the previous two terms in the sequence. So it starts 0 and 1. And then the next term you add the 2 before it, so 0 plus 1 is 1, and then 1 plus 1 is 2, and then 3, and then 2 plus 3, 5, 8, 13, 21, 33 it looks like, 54, and so on. Okay, we're going to label these entries with the position that they're in. So n is going to be the position that they're in. And we're actually going to start counting from 0 instead of from 1. So position 0 is going to be the number 0, position 1 is going to be the number 1, and then position 2 is also 1, position 3 is this 2 here, and 4, and so on. Okay, you can see it sort of takes a little while for the Fibonacci sequence to build up steam, but once it starts growing, it grows very quickly. So the thing about the Fibonacci sequence is that actually calculating it is kind of a pain, right? If you wanted to know for some reason what the millionth term, so n equals a million way out here somewhere, what the millionth term in the sequence is, you'd have to calculate every term in the sequence from the beginning all the way out to the end. And that can be rather annoying, not to mention computation intensive. So it would be nice if there were some sort of formula, some sort of general formula for the nth term of a Fibonacci sequence that would get us out of all of that work of calculating the intervening terms from the beginning all the way out to whichever term you're asking about, term n. So to do this, let's write down the relationship that produces the Fibonacci sequence. So the Fibonacci sequence, right, we can call f sub n is the nth term. So this means f sub 0, that's the number in position 0, and that was a 0. F sub 1, that's the number in position 1, and that's a 1. And then, right, these two numbers get the whole thing started, and then after that, to get the n plus second term, you add the two terms before it. So that's f sub n plus 1 and f sub n. Okay. Well, if we want to get all of our matrix algebra tricks into the game, we should try to rephrase this in terms of matrices somehow. And you know, it looks like this left hand or this right hand side is trying to be a matrix, right? It's as if we had a vector f sub n and f sub n plus 1, and then there's some matrix of coefficients, right? There are some coefficients here, and it produces f sub n plus 2. But right, if we start with a two-entry vector to begin with, then on the left-hand side we should also have a two-entry vector probably. And so what can we compute? Well, we're computing f sub n plus 2, but also, right, we have this extra entry, so we have to decide on what is the extra piece of information that we need to carry around. And it, you know, to compute the Fibonacci sequence, you have to carry around two adjacent terms. So if we have an f sub n plus 2, we should have an f sub n plus 1. So the coefficients here, those are 1s, so we need a 1 here and here. And now we need to write f of n sub 1 as some combination of f sub n and f sub n plus 1. Well, f sub n plus 1 is 0 times f sub n and plus 1 times f of n sub 1. So here is an equation that lets us go from one position in the sequence to the next position in the sequence. So, you know, for example, if we start with we won't start at the very beginning of the sequence, but remember, at some point in the sequence we had a 5 and an 8. Okay, so if we do this matrix product, in the first position we get 0 times 5 plus 1 times 8, that's 8. And then in the second position in this matrix product we get 1 times 5 plus 1 times 8, and that's 13. And the entries after 5 and 8 are 8 and 13. So, you know, this matrix is doing its job of taking us from one position in the sequence to the next position in the sequence. Now, the nice thing about phrasing it this way is we can imagine starting at the beginning of the sequence, which was 0, 1, and then, right, we know to advance to the next step in this sequence, we just multiply by this matrix, 0, 1, 1, 1. I'm going to call this matrix A. But if we, so this would take us to the next term, but to get from the second term to the third term, we would just multiply by this matrix again. So if we start with this vector that's f sub 0 and f sub 1, if we want to get out to the nth term, we just multiply by this n times, right? So that's going to give us, so if this is the 0th, then I guess this is going to give us f sub n and f sub n plus 1. Okay, so let me check that I have this right. If we plug in a 0 for n, then this is just the identity matrix times 0, 1, and that's 0, 1. Okay, and that's right. And if we plug in 1 for n, then f sub 1, f sub 2 should be 0, 1, 1, 1 times 0, 1. And this is 1 and 1. And that's right. Okay, if we wanted f sub 2 and f sub 3, then we would have 0, 1, 1, 1 squared times 0, 1. And what is this? Well, we'd have to work out this matrix product, right? What is 0, 1, 1, 1 squared? That's going to be, looks like 1, 1. And then over here we're going to have 1, 2. And then multiply that by 0, 1. And we get 1, 2. And yeah, this is the next. This is f sub 2 and f sub 3. So this formula is correct, but this actually isn't saving us any work because, you know, to compute, if we wanted to know the millionth term in the Fibonacci sequence, we would have to work out this matrix to the 1/millionth power, and that's just as hard, in fact harder, than computing all of the intervening terms of the Fibonacci sequence. So this equation here is true, but it's not helpful. It's not saving us any labor yet. But remember, one thing that diagonalizing a matrix does is it makes computing powers of the matrix very easy. So if we can diagonalize this matrix A, so 0, 1, 1, 1, if we can diagonalize this, so write it as p times some diagonal times p inverse, then raising it to the nth power will just be p times d to the n times p inverse. And since this matrix in the middle is diagonal, computing its nth power is actually very, very easy. Right? We can do that without doing just as much work as it would take to compute all of the terms of the Fibonacci sequence to begin with. So, so what we need to do is diagonalize this matrix. All right, well, to diagonalize a matrix, we have to find its eigenvalues, and then we have to find the corresponding eigenvectors, and so on and so on. So let's dive in. Let's find the eigenvalues of A. All right, so we need to find the determinant of lambda I minus A, or A minus lambda I, right? Those two things will have the same determinant. Those two determinants will have the same roots, the same zeros. So we need to take the determinant of so we got a lambda here, minus 1 here, we got a minus 1 here, and lambda minus 1 here. So this is lambda times lambda minus 1 minus 1. This is lambda squared minus lambda minus 1. Okay, now we need to know when this is 0. So we're going to solve lambda squared minus lambda minus 1 equals 0. This doesn't factor nicely, so let's just use the quadratic formula. We get lambda is 1 plus or minus the square root of 1 squared, which is 1, or minus 1 squared, which is 1, minus 4 times 1 times minus 1, all over 2. So this is 1 plus or minus the square root of 5. Okay. Now these numbers are actually sort of special numbers. They have special names. So the one with the plus, 1 plus the square root of 5 over 2, you might have seen this before. This is called the golden ratio, and the usual symbol for it is phi. So we'll abbreviate this with phi. And this other number with the minus, 1 minus the square root of 5 over 2, it's like the negative version of the golden ratio almost. It is a negative number since the square root of 5 is bigger than 1. But it's not just the negative of phi, right? In fact, you can check it's minus 1 over phi. Okay, so our two eigenvalues are phi and minus 1 over phi. So you can check that minus 1 over phi is equal to 1 minus root 5 over 2 just by taking this expression for phi, writing down its reciprocal, rationalizing the denominator, and it'll show up. All right, so we have our two eigenvalues. Now we need eigenvectors. So let's find an eigenvector for our first eigenvalue, which is phi. So we need to find the null space of a minus lambda I, or a minus phi I, right? The eigenvalue in question is phi. If you want, you can find the null space of phi I minus a. Those two matrices, they're negatives of each other, so they'll have the same null space. I just find it easier to write this down. So this is the matrix phi, 1, 1, and then 1 minus phi. Right? Yes. Okay. Now, something that is funny about this number phi is that it has all these special relationships, and in particular, 1 minus phi is one of them. So remember, phi is 1 plus root 5 over 2. So if we put this over a common denominator, 2 minus 1 plus root 5 over 2, what we get is we get 1 minus root 5 over 2, but this is our other eigenvalue. This is minus 1 over phi. Okay, so this is phi 1, 1, minus 1 over phi. Okay, now remember, we're finding the null space of this matrix, so let's row reduce it. I guess we can maybe take row, let's take row 2 and subtract 1 over phi times row 1. Okay, so that's going to leave row 1 alone, phi and 1, and this bottom left entry, so 1 over phi times phi is 1, so 1 minus 1 is 0, and then 1 times minus 1 over phi is minus 1 over phi, so why didn't this come out to be 0? I see. I'm missing a minus sign over here, so I need a minus sign here, I need a minus sign here. That means this minus here should be a plus. Okay. I need a minus sign here. And now when we compute this bottom right entry, now it comes out 0, right? Yes. Okay, there we go. So for an eigenvector, it looks like 1 phi is an eigenvector. All right, now for our second eigenvalue, this was minus 1 over phi. So for this eigenvalue, we have 1 minus our eigenvalue, which is minus 1 over phi, times I. So it's really a plus 1 over phi I. So this is 1 over phi, 1, 1, 1 plus 1 over phi. Okay. All right, and 1 plus 1 over phi. So, right, 1 minus root 5 over 2, that's negative 1 over phi. So plus 1 over phi is root 5 minus 1 over 2. So here's 1 over phi. Now let's add 1 to this, so add 2 over 2. And what we get is 1 plus root 5 over 2. So this bottom right entry here is actually just phi. Okay, so now we can row reduce this to find our eigenvector. I guess we're going to need to do row, let's do row 2 minus phi times row 1. That's going to zero out this bottom left entry. So 1 over phi 1, and then phi times this, subtracted from this is 0, good. And then phi times 1 is phi, subtracted from phi is 0, good. So that zeroes out this last row, and this means that our second eigenvector is, looks like it's going to be 1 and minus phi. So we can put a minus sign on either entry. I don't think it's going to make a difference, so let's put it there. 1 over phi. Okay, so now we have our eigenvectors. That means we can write, and our eigenvalues, we can write down our diagonal matrix. It's just the matrix with the eigenvalues on the diagonal, so that's phi and minus 1 over phi. And actually, why don't we make this one negative so that our eigenvalue shows up in this eigenvector, and we can write down the matrix that does the diagonalizing, which is P. P is just the matrix of the eigenvectors, so that's 1 phi and 1 minus 1 over phi. Now we need to write down the inverse, right? Which we could do by, augmenting P with the identity and then row reducing. But in the 2 by 2 case, there's sort of a nice shortcut for finding the 2 by 2 inverse. So what you can do is 1 over the determinant of the original matrix, and then on the diagonal you swap the entries, and off the diagonal you just add minus signs. So it turns out that always gives you the inverse matrix in the 2 by 2 case. So what is the determinant of P? Well, it's 1 times, let's write it out, 1 times minus 1 over phi, so that's minus 1 over phi, minus the other product, so minus phi. And then, so now we switch on the diagonal, so minus 1 over phi and 1, and then off the diagonal we put on minus signs, so minus 1 and minus phi. Okay, well, we should work out what this denominator is here. So minus 1 over phi, remember that's 1 minus root 5 over 2, minus phi, which is 1 plus root 5 over 2. And then when you simplify this, you just get the square root of 5. So this denominator is just the square root of 5. Okay, so that means our matrix A is 1, 1, phi minus 1 over phi, right, times our diagonal matrix, which is phi and minus 1 over phi down the diagonal, times P inverse, which is 1 over root 5 times minus 1 over, I'm sorry, this square root of 5, this determinant should have a negative, so there should be a minus sign right here. Okay, so minus 1 over phi, minus 1, minus phi, 1. And while we're at it, let's use the minus sign out here to flip all of these. So these are all pluses and that one's a minus. That seems like that might make our lives a little bit easier. Okay, now remember, the reason that we did this diagonalization was so that we could write down the nth power of A. So the nth power of A, remember, when you have a diagonal matrix and you raise it to a power, the matrices on the outside, when you write out the product, they just cancel on the interior. So they just sort of sit on the outsides like this. And this 1 over 5, 1 over root 5, let's move that all the way out to the front just to get it out of the way. So like this, minus phi, sorry, this is a plus phi now, minus 1. And then here, right in the middle, we get the nth power of the diagonal, but because it's diagonal, we just get the nth power of the diagonal entries. So phi to the n and minus 1 over phi to the n. All right, so this is the nth power of A. Now remember that the reason that we did all this was because the nth position and the n plus first position in the Fibonacci sequence was a to the n times 0, 1. And now we have a nice expression for a to the n. Well, relatively nice. It's this big mess here. So 1 over root 5 times 1, 1, phi minus 1 over phi times this diagonal, so phi to the n minus 1 over phi to the n times 1 over phi, 1 phi minus 1 times 0, 1. Okay, so now we just need to work out this matrix product. And you know, it's a little messy, but it's not that bad, so let's do it. It looks like it's going to be easiest to start all the way at the right, just because then we can take advantage of the 0 that's right there. So 1 over root 5 times, actually, why don't we do this product and this product at the same time? So both of these are going to be easy because on the second one we have that vector, but on the first one we have this diagonal matrix. So we get phi to the n plus 1, and then minus 1 over phi to the n, and minus 1 over phi to the n plus 1. Okay, and now for this second product, the matrix times the vector, that's going to give us a vector, column vector, and right, this 0 knocks out the phis. We just get this 1 and minus 1. Okay, so we get f sub n and f sub n plus 1. So, you know, what we really want is a formula for f sub n. So let's just work out the first entry in this matrix product. The second entry we don't really care about, so let's figure out the first entry. It's phi to the n plus minus 1 over phi to the n. I'm sorry, I missed this minus sign right here, so there should be a minus here. All right, so reading off the first entry, we get the nth term in the Fibonacci sequence is, so there's a square root of 5 in the denominator, and in the numerator there's phi to the n minus 1 over phi to the n. And remember that Phi is just the golden ratio, 1 plus the square root of 5 over 2. And minus 1 over phi is its negative sibling, 1 minus root 5 over 2. So this, this formula produces the Fibonacci sequence, which is kind of amazing because these numbers, phi and minus 1 over phi, they're both irrational, right? They both are built out of the square root of 5 together with some rational numbers. So they're both irrational numbers, but when you combine them in this particular way and divide by the square root of 5, the result is always an integer. Not only is it always rational, it's always an integer, which if you just looked at this formula and thought, if I plug in an integer for n, is this going to give me an integer? You'd probably think no. But in fact it does. It always produces an integer, and in fact it always produces the Fibonacci sequence. So this is a big surprise. You can see that this technique would work for any recurrence relationship, right? You could, so we had f sub n plus 2 equals f of f sub n plus 1 plus f sub n, but you can see we could make up any formula like this, like f sub, I don't know, n plus 3 is 2 times f sub n plus 2 minus 8 times f sub n plus 1, I don't know, plus 3 times f sub n. And you could make up any starting set of starting values, so maybe f sub 0 is 2, and they don't even have to be positive. F sub 1 could be minus 4, and f sub 2 could be, I don't know, 3, whatever. And this is exactly the input data we would need to do this whole diagonalization trick, right? In this case, our matrix A would be, let's see, we would be multiplying by f sub n plus 1, and f sub n plus 2, and we're getting the next terms in the sequence, so we need a 1 here, a 1 here, and then here's going to be our coefficients, so 3, minus 8, and 2, right? Zeros everywhere else. So to do the exact same trick to get a nice formula for the nth term of this sequence that I just made up, we would just diagonalize this matrix and then do all the same algebra that we just did for the Fibonacci sequence. So this way of using diagonalization of a matrix to get a closed form expression for this sort of discrete system where you advance time in discrete steps is actually a pretty powerful tool for modeling this sort of recurrence relationship. And there are lots of applications where this kind of recurrence relationship shows up. In fact, this kind of recurrence relationship is just a discrete version of a differential equation. So these same kind of tricks show up even when you're trying to solve continuous difference equations, which is what differential equations are.